Welcome students to our 1.4 Part 3 notes on a very important theorem called the intermediate value theorem. This theorem can also be abbreviated IVT, and I will abbreviate it that way throughout this video. This theorem is used quite commonly or tested quite commonly on the AP test, and for sure will be included on our Chapter 1, both formative and summative tests. It's a very, very important theorem, and so I hope that you will dedicate your time to really studying it and understanding it. Very, very, very important. Okay, now when you're talking about any theorem in calculus, it's important that you keep two things in mind. You want to keep in mind what the condition of that theorem is and what the outcome of that theorem is. So what is the condition for the intermediate value theorem? The condition is that the function we're talking about has to be continuous on a closed interval. So if ever you are proving anything that requires intermediate value theorem, you must always begin by confirming that the function meets the condition. Okay? What is the outcome of the intermediate value theorem? The outcome says this, that there will be some x value between the given interval of x's a to b, such that the corresponding y value will be between f of a and f of b. That's what this k is right here. Now, what does that mean? Well, first of all, we want to keep in mind that there's two intervals that we're talking about here. The outcome requires two intervals, and we want to keep in mind what those intervals are. We've got the x interval, which is the main part of the outcome. So you have your x interval from a to b, and then you've got this value c, which is between a and b. So the outcome says, okay, for some c, so that's right here, here's our interval a to b on the x-axis. For some outcome c, for some input c between a and b, if you trace that up to the graph, it will give you the value of a y value that's also between f of a and f of b. So we're calling that f of c because it's on the graph of f at the x value of c. So then that's the second interval, is the y interval. So we always want to basically keep the two intervals straight. So the y interval is between the corresponding y values, f of a and f of b. Now notice though, f of a is not always less than f of b. In fact, in this example, f of a is actually greater than f of b. So I'm going to write, or sometimes f of b is less than f of a. Now, k is in between those two. Okay, so k is a y value that is between the endpoints. And so actually the premise kind of begins with that k. It says, okay, if I take some y value, and I'm calling it k, but it's a y value between the endpoints, the y values of the endpoints, f of a and f of b. For some y value between f of a and f of b, I should be able to find, there exists at least one. I should be able to find one c value along that x interval between a and b, that the y value at c, that's f of c, is equal to this y value between f of a and f of b. Now, but what is that actually saying? There's a lot of complicated words going on there. What it's actually saying is that if f is continuous, right? Continuous means no holes, no jumps, and no asymptotes, essentially, is what continuous means. So that means f of a cannot skip down to f of b. It has to pass through every single y value that is between f of a and f of b. It can't suddenly have a hole where it passes over k. It can't suddenly have a jump where it jumps below k. And it can't suddenly drop off to infinity like an asymptote would. Essentially, this is saying that if f is continuous, it has to pass through all the y values on its y interval. So it's just choosing a generic one. It's just saying, okay, k is any y value between f of a and f of b. That basically is saying it's this entire interval. And for any value along this entire interval, the function has to pass through it. What does that mean, the function has to pass through it? That means there has to be an x value that if you plug it into the function, it will give you back that y value between f of a and f of b. Okay? But I want to point something out. It doesn't necessarily work the other way around. It doesn't necessarily mean that for every single x between a and b, f of c will be between f of a and f of b. Like, that doesn't always work. For example, if you look at like this value right here, that happened for an x value between a and b, but that y value up there is not in between f of a and f of b. So it doesn't work the other way around. I can't just pick any x between a and b and expect for that f of x to be between f of a and f of b. It only works going the one way. So you are able to choose any y value at all between f of a and f of b, and there will guarantee be at least one x where f of x equals that y value. It works that way, just not the other way around. Also, it's worth noting that it doesn't mean there's only one x. It just says there's at least one. Like if you look right here, that's a second x value, call that like a C2, that produces the same y. So, and then there's like another one over here. This one actually had 3. But IVT guarantees at least one, and that's all we really need to show typically when we're using IVT, is that there's at least one x on the x interval between a and b that produces this y value that's on the y interval. So what do we use the IVT for? We use it a lot to show that there are solutions to certain equations, especially when those solutions are hard to find and we don't necessarily want to find the solution. We just want to like know that there is one, and so we kind of analyze it against the intermediate value theorem. Now, I'm going to sort of ease you into that with example 1. Example 1 is not asking you to prove there's a solution. It's just asking you to check that the theorem applies so you can see how it works and actually go ahead and find the value. Now, that's something we don't typically ask you to do, but it is kind of a nice warm-up into understanding how this theorem works. Okay, so what does it mean for the intermediate value theorem to apply? It means that the condition has to be met. And what is the condition for the intermediate value theorem? The condition is that f of x has to be continuous on the closed interval a to b. Okay, so this function here is what we call a polynomial function because it's just x to different powers and different products of x and numbers and then being added or subtracted together. You could also think of this as a quadratic equation. So what we know about these functions is that they are continuous everywhere. But a quick recap of continuity says if a function is going to be continuous, then the limit as x approaches c for every c in that interval, so in this case that'd be 0 to 3, then that limit exists and is equal to f evaluated at c. So these two things have to exist. F of c has to exist, the limit has to exist, and they have to be equal. So just a quick glance over here at the actual graph, right? It's going to be a parabola, and these functions have no holes, no jumps, no asymptotes. For every c value, not even just between 0 to 3, but for every single c value on the real number line, these conditions are all met. The two-sided limit exists, and the function is evaluated at the same point all along there. The limits equals the value of f all along. So it's sufficient enough to say, since this is a polynomial or even just a quadratic function, you can say, since f of x is maybe I'll just call it that, is a quadratic function, it is continuous on the closed interval 0 to 3. Okay, but then what else has to happen for it to apply? Well, here, so that is the first thing we check for is continuity. So we check for continuity. continuity. Because if the function's not continuous, you can forget about using IVT. It's not going to work. It only works if the function's continuous. But in this particular case, it also mentions that it wants to know if there's a point where f of c is specifically 0. So the second thing you want to check is if the y value in question, so is k, I'll call it, is at between f of a and f of b. You kind of want to check your y interval. So thing 1, the function is continuous, that was met. Thing 2, we're going to check the y interval. So we have to evaluate f of a, which in this case is f of 0. And that gives me 8. And then we check f of b. So we have f of 3. That's negative 9 plus 8, so that's negative 1. So this is my y interval right here. So just to clarify, my y interval is negative 1 to 8. Okay, so my x interval is 0 to 3. My y interval is negative 1 to 8. And yes, 0 is between those y values. So that's the second thing that has to happen for the theorem to apply. So the function was continuous, check. The k value that they gave us, which is 0, is between f of 0 and f of 3, which was negative 1 and 8. So now we know that for sure there is a c, there is an x between 0 and 3 where the y value is 0. So now in this case it just says, okay, go ahead and find it. So instead of proving that it exists, we can just go ahead and find it. So the way you find it is by taking the y equation and setting it equal to the given y value, which in this case was 0. So now we're just basically solving a quadratic equation. And we can go ahead and solve this one by factoring. So I see that I can factor it into x minus 2 and x minus 4, since those numbers add to negative 6 and then multiply to positive 8. And then I can take each of those factors and set them equal to 0. So I get 2 answers. But it's only looking for the one that's between 0 and 3. So that will be the 2. So then I can say, yes, IVT applies, and C is equal to 2. So again, to show that IVT applied, I had to state that the function was continuous. I had to show that the given k value, which was 0, was in between f of a and f of b. To find it, I just solved an equation. What I'm really interested in doing, though, in this video is showing you how to prove something effectively using intermediate value theorem. Notice here in the instructions, it doesn't indicate at all what theorem you're supposed to use. So how do you know you need to use intermediate value theorem? It's because we're trying to show that the function has a particular value. So you use IVT whenever you're asked to show or asked to prove that a particular f of x value exists. Okay? Now, look out for a question asking about this on the quiz this week. I'm going to say, what do we use IVT for? We use IVT to prove, or whenever we're asked to prove that a particular y value exists. Notice here it is not asking you to find the y value, because we would have to do that graphically. There's no analytic way here to find the y value. We can look at a graph, which I'm going to show you in a moment, and see that it does in fact have a solution, but instead of finding it, we're going to just prove that it exists. Okay, so how do we begin to do that? First, we look for the conditions of IVT, okay? Which is that f of x has to be continuous And in this case, the interval is 0 to 1. So that's my x interval. It has to be continuous on that interval. And the given y value, which they didn't give a y value, but they said has a root. I don't know if you remember what that means, but has a root means that the y value equals 0. So the given y value of 0 must be between f of a and f of b. So we have to check those two things first. Okay, so what do you notice about this function? I hope what you're noticing is that it's a polynomial. It's another polynomial function. These functions are understood to be continuous everywhere. So you would begin by saying the following. Since f of x is a polynomial function, it is continuous, and you always want to include the closed interval. On the closed interval 0 to 1, we indicate a closed interval with brackets. Okay, so you always want to start by mentioning continuity. Okay, on the intermediate value questions, if you don't mention continuity, then you lose a point. Okay, you got to begin with the condition. And since we're going to go ahead and find f of 0. So f of 0 is 1, right? 0 cubed plus 3 times 0 is 1. Or sorry, plus 1 equals 1. And since f of 1, so we have 1 cubed minus 3 times 1 plus 1. So that's negative 2 plus 1 equals negative 1. So and since f of 0 is 1 and f of 1 is negative 1, that means that 0 is between f of a and f of b. So it looks like it's between f of 1 and f of 0. Right? F of 0 was 1, f of 1 was negative 1, and 0 is between those. So what does that mean? Well, by IVT, so I'm abbreviating the theorem here, there must exist, you can either say, a c or an x. There must exist, I'll just put a c value, between 0 and 1. So the value that you are stating must exist is an x value. So there's an x value between 0 and 1 such that f evaluated for that particular number, which we never did find. We just know that it's somewhere between 0 to 1. Somewhere between that x interval. Somewhere between there, the y evaluated at that point has to equal 0. Okay, so let me just so that's what you would say. That's your answer. That whole paragraph is your answer. You start with the condition that it's continuous. Let me kind of point out the important parts here. So you start by showing it's continuous on the interval. You're going to state that interval twice. You then have to find the y interval and be kind of redundant here and show that the y value in question is in between it. You want to reference the name of the theorem. And then here's where you state your x interval again. You say, okay, there's an x value back on that interval. You say it twice, such that y evaluated at that number would give you the one we're trying to prove exists. So this is what it meant to prove there's a root, right? Here's a root of f of x is when f of x equals 0. Okay, so that's the y value that we were trying to show existed. This is the x value that we never did find, but we know exists. Okay. And we stated that x interval twice. First here, when we were showing it's continuous. You state the interval. And then again, when you're showing where that x value exists, you state that x interval. In the middle of the theorem is where you address the y interval. Okay, so you have to find it first. You find it and then you state it. Right there is your y interval. And what should happen in order for this to work is the k value in question, or the y value that they were asking you to find, this guy right here. Y value that you need to prove exists. You make another interval where you show, hey, look, that's in between my y interval, which I just found, right? -1 to 1 is my y interval, and the y that I'm trying to show exists is in that interval. Therefore, IVT guarantees an x on my x interval. That f of that x would give me that y value in my y interval. Okay, so let's confirm that with the graph. So what you should do with all of these is graph them to kind of visualize what's going on. Where is my x interval? I'm going to zoom in here. My x interval was between 0 and 1. So that was here to here. Okay, that's my x interval. My y interval was between -1 and 1, here to here. And so 0, of course, is between -1 and 1. And sure enough, there's my c value. My c value is this decimal, right? Some decimal between 0 and 1. I can see for a fact that the function does in fact pass through 0 between the x interval of 0 and 1. So that's kind of what's happening there. And then this paragraph is proving that. Okay, I'm going to show you one more of these, and then I'll have you try one. Now in example 3, it's a little even more vague. Show there is a solution. That's pretty vague. Show there is a solution to the following equation on the interval 1 to 2. So this often really throws students for a loop because they start trying to solve this equation, because that's usually what we do when we're being asked to show a solution, is we find it. But this is not saying find the solution. It's saying show there is one. So we're going to use IVT for this, but let me show you how we structure it. Here's what I suggest you do. I suggest that you go ahead and, instead of having two separate equations, form a single equation where you have a difference between those two functions. So you essentially subtract one function from both sides, so that on one side you have a 0, and on the other side you have a new function. This is going to help you use IVT. So what we're really trying to prove is that at some point this new function takes on a y value of 0. So it ends up being similar to the equation we just did, but we had to make it happen. So here's what we would do. We would start by saying, let f of x, or whatever you want to call your function, equal x squared minus the square root of x plus 1. Okay, so we first establish a new function. Now you got to check, is this function continuous? Because we always have to start with the conditions. Well, I'm going to let you take a couple shortcuts here because the AP test does as well. X squared is a polynomial function which is continuous. And the square root of x plus 1, the square root function is a radical function, which as long as it's defined is continuous, and it is defined between the x's of 1 and 2. So this is what we say. We'll say f of x is continuous on the closed interval from 1 to 2, since x squared is continuous on the closed interval, and the square root of x plus 1 is continuous on the closed interval. Therefore, the difference between the two functions, that was one of our properties of continuity, the difference of these two functions will be continuous on that interval as well. Okay, so we start with the condition, this difference of two separately continuous functions is also continuous by the subtraction property of continuity. Okay, and you don't have to say that last part. You can just say it's the difference of two continuous functions, so it's continuous as well. Now, what we need to show next is that this y value is on the y interval. So this 1 to 2 is my x interval. What I need to do now is find the y interval. So I'm going to say, and since f of 1, and then I evaluate that at 1. Oops, sorry, it's minus. Now the square root of 2 we know is greater than 1 because it's greater than the square root of 1, which is 1. So we know that this value is less than 0. So f of 1 is less than 0. And f of 2 now we know the square root of 3 is less than 4 because the square root of 16 is 4 and the square root of 3 is less than the square root of 16. So that means this number is larger, so when you subtract a smaller number, it's positive. So since f of 1 is negative and f of 2 is positive, that implies that 0 is in between them. 0 is in between f of 1 and f of 2 because 0 is in between a negative number, which is what f of 1 is, and a positive number, which is what f of 2 is. So we know the function's continuous. We know that 0 is a y value that falls between the endpoints. So that implies, so therefore, by IVT, this is where we state our x interval a second time. And maybe I'll just call it x. There exists an x on the interval from 1 to 2 such that f of x equals 0. Because IVT, that's what it states. It says if you can find a y value in between the two ending y values, then you're guaranteed an x that if you plug it into the function will equal that y value. That's what IVT guarantees, so that's why you can state it here. This shows that for some x in the interval 1 to 2, x squared must equal the square root of x plus 1. Because when you show that the difference between two things is 0 at some point, what you're essentially showing is that they must have the same value at that point. So you kind of want to come back to that, tie it all together with the original thing you were asked to show. But that's the general process when you're asked to find or show if there's a solution to an equation. You subtract 1 from the other side to make a new function equal to 0. You treat that 0 as your k value, if you will, the y value that you're trying to show exists. Prove that it equals 0 by IVT, and then bring it all home by saying, okay, if this function, which is the difference of these two functions, equals 0, then for that same x in the interval 1 to 2, then those two separate expressions must be equal to each other. Okay, so now let's go ahead and confirm this with a graph just so you can see how that works. So there's two ways you can check on a calculator, and you can sketch this on your paper too. So basically what I did is I just sketched the graph of each function, the x squared, which is on one side of the equal sign, and then square root of x plus 1 on the other side of the equal sign. And here's our interval 1 to 2, right on the x-axis. And you can see right there is the point where they are equal to each other. So there is an x value, 1.221, where the x squared function equals the square root of x plus 1 function. That's one way to check and just to make sure the solution's there. The other option would be to use the new function we made, the x squared minus the square root of x plus 1, and see where that is equal to 0, right? Because when you subtract these two, if we're trying to find when they're equal and you're subtracting two equal values, you'll end up with a 0. So you can see it's that same x, 1.221, which is between our interval of 1 to 2, that it produces a y value of our new function of 0. So why don't you guys try this last one here, pause the video, try this one out, come back and check it when you're done. Okay, so I have two options for a solution to this one because there's really two routes you could have taken. The first route, which I have here as option 1, is if you leave the equation as is and choose this first part to be your f of theta. So f of theta would equal tan theta plus 3 theta. And then the k value that we're trying to prove exists, which is that y value. The y value on the y interval that we're trying to show exists would be 4, would be whatever this function equals. So we go through the process. So first we have to sort of define your function. Okay, so that's kind of the first thing we do if it isn't already defined elsewhere. Then you show that that function's continuous. So we know that on the interval 0 to pi over 3, tangent does not have any asymptotes there. So tangent and 3 theta are continuous, like as separate functions. This would just be a straight line. And this is the continuous function that looks like this, right? When it doesn't have any asymptotes, it just kind of makes a squiggly shape. So between 0 to pi over 3, it doesn't have any discontinuities. So tangent and 3 theta are continuous functions separately. So when you add them together, you take their sum, that's f of theta, then that will also be continuous. So we establish continuity, which is the condition for the intermediate value theorem. So we define the function. We show that that function's continuous on the given interval. Then we go to work trying to find the y interval. So we have to find the endpoints, f of 0 and f of pi over 3. So it's 0, and then this value right here. So suppose you had this on a non-calculator part of the test, and we don't necessarily have an exact value for the square root of 3 or pi, but we do know that pi is approximately 3.14. So it's a little bigger than 3. And we know that the square root of 3 is bigger than the square root of 1, which is 1, right? So we know that this number is something bigger than 1. We know pi is a little bigger than 3. So if you add that together, what we do know is that it will be greater than 4. Like that much we know. Okay. So what have we established? We have established that the y value we're trying to show exists does in fact fall between the y interval. It's between the endpoints f of a and f of b. So that's where IVT definitely applies. We show the y interval, we show the k in between the endpoints. Then we make our concluding statement. So these are the main things you want to show. Therefore, you want to reference IVT. You state, again, there must exist some theta. This was acting like our x value on the interval 0 to pi over 3. That's our x interval, or our theta interval in this case, where the function must equal that k value, must equal this value up here that we were trying to prove exists. So that's option 1. Just a quick side comment as well. When you see this variable theta, you can treat that like x. It's basically a Greek letter that we use to be a variable when we're dealing with angles. So it's a variable just like x is. So you treat it like x, but typically it's used in like a trig context where we're working with angles, which is what these are, 0 and pi over 3. So theta is acting like x. So that's why 0 to pi over 3 is our x interval, which is why we state it twice. Remember, you always want to state that x interval twice. So that's option 1, is showing that the function equals 4. Option 2 could be done like the last example, where you subtract 4 from both sides, and therefore your function would be this whole thing, tan theta plus 3 theta minus 4. And since when you subtract 4, you get 0 on one side, then in this scenario, the k value that we're trying to show exists is 0. 0 is the y value that we're trying to prove. So you start the same way. You define the function. tan theta plus 3 theta minus 4. You say, let's call that f of theta. You then go on to state that these three functions separately, so this is that trig function that just makes a squiggle, this is a straight line, this is a horizontal line. These are all separately continuous on the interval 0 to pi over 3. So there's the first time we mentioned that x interval. So then when you put them together, you add or subtract them, which is what f of theta is. That means f of theta is also continuous on that x interval. So we define the function. We show that it meets the condition, that it's continuous on the interval 0 to pi over 3. Okay, then we go to work finding our y interval. So I find f of 0, which equaled -4. And then I find f of pi over 3, which ended up equaling this, rad 3 plus pi minus 4. Now again, I don't exactly know what that equals, assuming I don't have my calculator, but I know that rad 3 is greater than 1, and I know that pi is greater than 3. So if you add these together, overall, it's going to be, these are going to be greater than 4. So when you subtract 4, you're going to have a positive number, a number greater than 0. So what does that mean? That means that 0 is in between my endpoints. It does fall within the y interval. So you want to state the y interval right here. So then the conditions are met. The function's continuous, and the y value we're trying to show exists does in fact fall between the two y endpoints. So that's enough to then just make your statement. So we start by saying, therefore, by IVT, reference the theorem, there must exist that theta, that's acting like our x, on the theta interval, which is like our x interval, such that f of theta is 0, right? The function we defined does in fact equal 0. So what does that imply? That implies that the first half of it has to equal the second half, right? Because if you show that the difference between two things is working out to be 0, what you're really showing is that those two quantities, so this part and that part, are equal. That's what that really shows, which is what the question was originally asking for. So I wanted to show you how to confirm this with the calculator, both option 1 way and option 2 way. So here I am looking at the option 1. Option 1 is when you treat tan theta plus 3 theta as a separate function, and then 4 as the y value that we're trying to show exists. Also, I'm just going to show you where pi over 3 is. It's right about there. So you can see that there is in fact a solution right there that is between 0 and pi over 3, right? There is a point where tan, and notice here I typed it in as x. So if you're using a graphing calculator or Desmos, you can't, if you type in theta, it's not going to recognize it as x. That's just something we have to understand, that theta acts like x. So when we type it in with x. So tan x plus 3x does in fact equal 4 at this value 0.907, which is slightly greater than pi over 3. So that's option 1 method. And then the option 2 method is when you go ahead and subtract 4. And so you look instead for where this function is equal to 0, meaning where it hits the x-axis. And so we see that same solution again, the 0.907, is where this other different function where we subtracted 4 from would in fact create a 0, and then you do see right here there is a place where it equals 0 between 0 and pi over 3. So that tells us that we do know for sure there is a solution there, and then the IVT is what we use to like analytically prove that. And that concludes our video on the intermediate value theorem.